Page 1, question 7. Okay, so this one is June 15, P42. Question 7. Okay, right. So they tell you you have a solenoid that's connected in series with a resistor here, as shown in figure 7.1. As the magnet is being moved into the solenoid, thermal energy is transferred in the resistor. Use laws of EM induction to explain the origin of this thermal energy. Okay. Why is it that when I move the magnet, which is this one, into my solenoid, which is this one, I suddenly have thermal energy inside the resistor? Okay, right. So this one, you can actually kind of explain it in a number of ways. Either you explain it in terms of energy or either in terms of force. Let me just explain it in terms of force first, in terms of Lenz's law. Okay, right. So if I have a magnet here and I move it inside the solenoid, you could say that you have change in flux linkage, because you see your magnet in itself already has its own magnetic field.
Okay.
Okay. So when you move your magnet into your solenoid, you're causing a change in flux linkage. Before this, you see your flux linkage here is 0. When your magnet is far away, your flux linkage is 0. But then after that, once you move your magnet in, your flux linkage is going to be some value lah. All right. So you have change in flux linkage. You therefore have EMF induced. Okay. Now, so when you have EMF induced, when EMF is induced, when voltage is induced, current is also induced. Okay, they are both closely related to each other. If you have induced current, it must mean that you have induced EMF. Okay, so when EMF induced, I know that I have current induced. So now here's the thing. If my current is induced inside the solenoid now, I can have a case where my current either flows like this in the counterclockwise direction, or either it flows like this in the clockwise direction. So which one is actually the correct one? This one has to be related to current, to Lenz's law. We did this in the last lesson. We mentioned that Lenz's law will always flow in such a way to prevent the flux change that caused the current in the first place, right? So right now, let's consider this now. If my current is flowing counterclockwise, like this, counterclockwise like this, my direction of my magnetic field would be in this direction, right? This one will be my north pole, this one will be my south pole. Okay, so is this going to be correct if you think about it? Would this help me to prevent the flux change, or would it cause the flux change to become worse?
It would cause the flux change to become worse.
It will cause the flux change to become worse? Okay, now, what is the nature of your flux change first? The nature of your flux change is an increase in flux linkage or a reduction in flux linkage that caused the induced current?
An increase.
An increase, right? So this one right now, you look at it, if my current is flowing in the counterclockwise direction, this one is north, this one is south. This induced current flowing through my solenoid will cause a magnetic field to be produced inside the solenoid itself. So at that point, when you try to push in your magnet any further, there's something opposing your magnet from going in, right?
Yep.
isn't this opposing your increase in flux linkage? Isn't
Okay.
this opposing your flux change that caused the induced current in the first place? So this
Okay.
one is actually correct, right?
Mm-hmm.
So if I consider it the other way around, let's just say I tell you that my current is flowing counterclockwise. Sorry, my current is flowing clockwise right now. Okay, my current is flowing clockwise, such that my polarity of the magnet is south and then north here. So in the case that this one is south and then this one is north, the magnetic force acting on my magnet will be in this direction. This one is actually trying to pull the magnet in even further. It's actually going to cause an even larger increase in flux linkage. It's actually making things worse. Okay, it isn't opposing the flux change. It's actually supporting the flux change. It's trying to make it even bigger. So this one will be the wrong one. Okay, right? So that was the essence of Lenz's law lah. So here, because of Lenz's law tells you that your direction of induced current will be such as to oppose the flux change that causes it. It produces a magnetic field to oppose the motion of the magnet. Okay, so if your motion of your magnet is being opposed, if you want to keep pushing your magnet into your solenoid to produce an EMF, you need to do work to move the magnet into the solenoid. So the work that you do goes into the work done goes into the electrical energy of your induced current, and it goes into the thermal energy of your resistor. You see, the thing here is that when I have induced current flowing, my induced current is flowing through my resistor. And when current flows through resistor, it tends to dissipate heat. So basically what the question is asking you right now is that they're actually asking you to explain the origin of this thermal energy. Where did the thermal energy actually came from? It actually came from the electrical energy of your induced current, but at the same time, it also came from your work done in the first place. Okay, your work done went into the electrical energy of your induced current, which in turn went into the thermal energy of your resistor. Okay, so that's why your answer was like this.
Okay. Right.
The moving magnet induces an EMF in the solenoid. This gives rise to an induced current that creates a magnetic field that opposes the motion of the magnet. This one is actually Lenz's law, the effect of Lenz's law. Okay, thus work is done to move magnet into solenoid. The induced current causes heating effect in the resistor, which comes from the work done.
Okay.
Okay, right. Now, there could also be other ways to explain the same thing. This one is like explaining it in terms of purely energy point of view. That one is the statements that are written in red below. So the first two statements are actually the same. Solenoid here, okay, this one here I say that the solenoid cuts the magnetic flux of the moving magnet. Rather than saying that there's a change in flux linkage, I can also say that the solenoid is cutting the magnetic flux of the magnet. It also works just as fine now. Okay, this in turn causes an induced EMF in the solenoid according to Faraday's law. The induced current flows through the resistor, and this causes heating effect. The thermal energy comes from the kinetic energy of the moving magnet. Okay, this one is just really explaining it just purely from a energy point of view. You can also do that lah. Okay.
Okay.
But the ones that is written in pencil here is actually the marking scheme answer. Okay, so that one is okay. Then after that, I will move on to another one. All right, so this one okay. I move on to page 6. Okay, page 6 will be this one. Okay, page 6, I need to explain it a little. Okay, page 6, June 16, P41. June 16, P41. All right, so now if you look at this one, okay, now page 6, question 10 there. They tell you that you have a core insulated wire that is wound on a copper core as illustrated in figure 10.1. An alternating current is passed through the core. Okay, alternating current is passed through the core. The heating effect of the current in the core is negligible. Explain why the temperature of the core is rising. Okay, explain why the temperature of the core rises as a result of you running an alternating current through the core. Okay, now this one here, there are just some things to note here. You have your copper core, which is the green colored thing here that I highlighted. And then at the same time, you have your insulated wire, which will be the blue colored things that I kind of highlight here. Okay, right? You actually have two different objects here, copper core and insulated wire. Okay, now this wire is insulated. Now, the thing that some people would think of is this. You see, when current flows through wire, it heats up, right? Okay, because of heat dissipation. Because of heat dissipation. Okay, so when current flows through wire, it heats up because of heat dissipation. Then after that, if we tell you if the wire is in contact with another conductor or metal, it also heats up. This one is sensible, right? Here, if I tell you current flows through wire, the wire will heat up because of heat dissipation. And if the wire is in contact with another conductor or metal, it will also heat up. All right, correct? So now here, you're having a case where you have wire in contact with copper wire. But now they're asking you to explain why the temperature of the core rises, the copper core rises. You're explaining why is it that the copper core is heating up. Okay, so if you want to explain why the copper core is heating up, you cannot use this explanation over here. You cannot say that, oh, because current is flowing through the wire heats up, and then because it's in contact with the copper core, the wire also heats up.
Okay.
Sorry, because it's contact with the copper core also heats up. The question already specifically mentioned to you, don't do that, because you see here, they tell you the heating effect of current in the core is negligible. So this one here, you are not assuming that the wire is heating up, because sometimes people will say, oh, the wire heats up because it's in contact with the copper core, it also heats up the copper core along with it. But here they already specifically tell you, don't assume that the current in the core does not cause any heating effect. And at the same time, they also tell you that this thing is insulated. So even if, let's just say in the unlikely event that your wire heats up, the heat cannot pass through the copper core because it's insulated. Okay? That's why I say this explanation here, you cannot use. You have to explain it a different manner.
Okay.
Right? Okay, so how do you explain this? Now, when they tell you you have alternating current, just now I mentioned to you alternating current looks like something like this. Current of I versus T will look something like this. And because flux linkage is proportional to current, a graph of flux linkage versus time will also look like that same shape there. Okay, so right now, I know that when current flows through my wire, it's going to produce a magnetic field, which in turn produces a flux linkage. Okay, you're going to have a magnetic field. The magnetic field passes through your copper core. Okay, your magnetic field passes through your copper core. But then the magnetic field itself doesn't remain constant because your current changes. Okay, your current changes, your flux linkage will change. You could also say that your flux also just changes because I is also can be said as proportional to flux. Okay, it doesn't matter which one you want to assume. I is also proportional to flux. Okay, so when my current changes, my flux through my copper core will also change. Okay, so because the copper core experiences a change in flux, my copper core would start to have induced EMF. So when I have induced EMF, I'm going to have induced current. So the current flowing inside my copper core will actually cause the heating effect. That's why the temperature of the core rises. Okay, that's why you see your answer was something like this, where they tell you the alternating current through the alternating current causes magnetic flux through copper core to continuously change. So since the magnetic flux is changing, this induces EMF in the core according to Faraday's law. So because you induce EMF, you now have current forming in the core, which will give rise to your heating effect. Okay.
Okay.
Okay. So this is one thing here. Earlier, I mentioned to you in Faraday's law that your EMF is induced either through flux cutting or flux linkage change, right? Okay. So in the previous lessons, I told you that Faraday's law is where you have EMF induced either through flux cutting or flux linkage change. Sometimes this can be generalized as just this. When you have change in flux, as long as something experiences a change in flux, you're going to have EMF induced. The reason why I'm mentioning this now here is because you see your copper core, it's not correct to say that your copper core experiences a change in flux linkage, right? Because it's not a core. So I cannot say flux linkage change. And then at the same time, you don't see your copper core moving across the magnetic field. So it isn't really cutting a magnetic flux. Instead, what's happening here is that the flux through it is changing. So it's more accurate to say that there's a change in flux law. Okay.
Okay.
So in the first place, flux cutting or flux linkage change can be generalized as just change in flux. As long as anything experiences a change in flux, you're going to have EMF induced. Okay, so that one is okay. Okay, so that one, all right. Then after that, I move on to part B. Okay, part B is somewhat related to Lenz's law also, but this one I think I can do this quite okay. All right, now look at part B. They tell you two hollow tubes of equal length hang vertically as shown. Okay, one tube is made of plastic. The left hand tube is made of plastic, and the other is aluminium. That is the right hand tube. Two similar bar magnets A and B are now held above the tubes and then released simultaneously. The magnets don't touch the sides of the tube. Explain why magnet B would take a much longer time than magnet A to fall through the tube. Okay, so they're really just asking you right now, why does it take such a long, why is it that magnet B, the one that falls through the aluminium tube, will take a longer time than magnet A to fall through? Okay, the answer for this, you have two different explanations, either through a force explanation or through an energy explanation. So before we go to that, let's have a look at the explanation first. Okay, now we look at the diagram below here that I just drew. Now, if you're talking about magnet A, which is just the plastic tube, okay, when the thing falls, do you think that there is any induced current when magnet A falls? I know that magnet A would have its own magnetic field here, but when it falls, would there be any EMF induced inside the plastic tube? Plastic tube is an insulator, mind you. Would there be any induced current? Can current flow inside an insulator?
No.
No, right?
Yeah.
So here you have a plastic tube, although you can say that yes, the plastic tube is cutting the magnetic flux of the magnetic you can, although here you can say that the plastic tube is cutting the magnetic flux of the magnet as it falls. There's no current flowing because it's an insulator, right? So there's no induced current. So in my case here, my magnet A doesn't have any induced current. There's no magnetic force whatsoever trying to oppose the motion of the magnet falling, according to Lenz's law. Lenz's law won't come into play here in the first place because you don't have induced current in the first place. So what will happen is that your magnet A, as it falls, it will always just experience weight W. Okay, nothing, it will just always experience weight W. Okay, so its acceleration would always just be equals to G. Okay, in general, one thing I'll just mention here is this. Now, this one is actually something from the AS physics. If the only force acting on a falling object is just the weight, then, sorry, I have to write things properly. If the only force acting on a falling object is just the weight, then A will be equals to G. Okay, so here my object is always experiencing just the weight. There's no other force acting. Its acceleration will always be equals to G. Okay, simply put lah. Right?
Okay.
Now, when you look at magnet B, this is where things start to become a bit different. If you look at magnet B, the one that is made out, when you look at magnet B that is falling through the aluminium tube, I know that my magnet B has its own magnetic field. So when it falls through the aluminium tube is cutting the magnetic flux of magnet B. And because aluminium is a conductor, you're able to have induced current. You have EMF induced, you have induced current, right?
Yes.
All right. So now, Faraday's law tells you that you have cutting of flux, so you have induced EMF. So from induced EMF, you have induced current. Now, when you look at induced current, Lenz's law tells you that the direction of your induced current will be such as to oppose the flux change that causes the induced current in the first place, right? Correct? Now, let me just ask you this now. When your object was moving from here to here, this according to the green arrow that I drew there, what is the nature of your flux change? Is it increase in flux cutting or decrease in flux cutting?
If it's the scenario on the
This
left,
one.
is it? Okay.
Yeah, this one. Is in my case, I know I'm cutting of flux, but is it a case where I'm cutting more flux that cause the induced EMF, or cutting less flux that cause the induced EMF?
It's cutting less flux because of opposing.
No, it's cutting more flux, right? As my magnet fall, as my magnet fall all the way to here, my
I mean, there's more.
Aluminium tube is cutting more flux in the first place, right?
Yes, yes.
Okay. So here,
The direction, I mean the poles of the magnet doesn't matter.
yeah, the poles of the magnet will try to oppose your flux change. So now before I go to that, I just want you to see what was the nature of your flux change here.
Oh,
As
okay.
your
It will cut more as
yeah,
it
the
falls.
nature of your flux change here is that is increase in flux cutting, right?
Mhm.
So Lenz's law will tell you you want to reduce the flux cutting, correct? So I know that I have induced current that's flowing through my aluminium tube over here. That induced current will have a certain polarity. According to Lenz's law, it will be in such a way to oppose the flux change that caused the induced current in the first place. In my case, I have increase in flux cutting that caused the induced current. So my Lenz's law will tell me that my current will flow in such a way to produce a magnetic polarity that will oppose the increase in flux cutting. So the only way that can be done is if my current flows in such a way that this is the north, this is south.
Mhm.
So if it is that case, as the magnet tries to move in, it experiences a magnetic force trying to prevent it from coming in.
Yeah.
So this one is trying to, this one is as a consequence of Lenz's law, decrease the flux cutting, right? So that's why my polarity is N and S here to oppose it. Okay, so far so good?
Yep.
Okay, now then after that, another thing here would be this one. As my magnet already went into the tube and then it's about to fall out, you look at the scenario on the right here, my magnet now tries to move out, okay? If I look at this part here from here to here, as my magnet tries to leave, I will actually have a decrease in flux cutting, okay? Because my magnet is now trying to move away from the tube, my tube is actually going to cut less flux already, right? So this one, decrease in flux cutting will still cause EMF, will still cause induced current. So according to Lenz's law, the direction of the induced current will again flow in such a way to prevent the flux change that causes it. In my case, my flux change is a decrease in flux cutting that caused the induced current. But Lenz's law tells me that my induced current will try to oppose this flux change. So if it is decreasing right now, my induced current will flow in such a way to try and decrease the flux cutting. In other words, it will try to increase back the flux cutting. So in this sense here, my induced current will flow in such a way that this is north, this is south. You see, when this is north, this is south, this north and this south, they attract. So the magnet will experience a magnetic force trying to pull it back in. It's trying to cause the decrease in flux cutting to become less. Because now my EMF is produced due to decrease in flux cutting, you're trying to prevent it from decreasing. So you're trying to increase it back. So that's why here, your induced current will flow in such a way, such as to suck the magnet back in. Okay? Right? So you see, going in, you have one direction of induced current. Going out, you also have one direction of induced current. It's basically trying to oppose your magnet from coming in. It's also trying to oppose your magnet from going out. Okay? Now, from here, you can actually see one thing. As my object is falling, maybe I better just draw it on the right hand side here. As my object is falling, I have weight, and then I also have magnetic force trying to oppose it. Here you see it's trying to oppose me from coming in. Here it's trying to oppose the magnet from going out. If I apply F net equals to MA, this one will be if I just look at this one itself, maybe I just look at this one. This one, my net force was W. This one, my net force is W minus FP. Okay, this one here is where my net force is W minus FP. Now, which one do you suppose is having the lesser net force here? This one or this one? The left one or the right one? If you just look at net force alone. Here, net force is W. Here, net force is W minus FP. Which one do you think is going to be the lesser one? Okay, let me give you a hint. This one is weight. This one is weight minus of some force. Obviously, this one is going to be less, right? For the net force. If I tell you that this is 100 Newton, this one is 100 Newton minus 20 Newton, I'm going to get 80 Newton here, right? So my net force is actually going to be less on the right hand side. Okay. So here, my net force has dropped. My acceleration will obviously drop. So this one is actually moving slower than this. If I give you A equals to 9.81 meter per second square versus A equals to say 3 meter per second square, which one will actually be moving slower, the left one or the right one? This one will actually be moving slower, right? And then this one will actually be moving faster, right?
Yeah.
So if you have something that's moving slower, do you think it would take a longer time to fall or shorter time to fall?
I think it will take a longer time to fall.
Yes. So if the thing is moving slower in the first place because the acceleration is smaller, it will take a longer time to fall. Okay. So this particular portion here, the main thing just to understand was that as your magnet tries to fall in the magnet and tries to go out, there will always be a magnetic force trying to oppose its motion. That in turn causes your net force to become less, your acceleration to become less. It will therefore move slower. So because it moves slower, it will actually take a longer time to fall. Okay.
Okay.
Right. Yeah. So this one, yeah, I mean, when I explain it, I'm trying to explain it step by step. It may seem a bit confusing, but then after that, when you look at the answer scheme, the marking scheme answer, it's actually pretty straightforward. You can see why. Okay, so let's have a look at the answers. There's actually two different answers. The first one is this one. This one is based on force explanation. So here, let's look at this sentence by sentence. As the magnet falls, the aluminum tube will cut the magnetic flux of the bar magnet. This causes an EMF to be induced in the aluminum tube. Currents form in the tube that causes heating of the tube. Oh, sorry, this one is not force explanation, my mistake. This is energy explanation. My mistake, sorry. This is energy explanation. So eddy currents form in the tube that causes heating of the tube. When current flows inside a conductor, it tends to heat up. So that's why I say here current form in the tube causes heating of the tube. This heating takes energy from somewhere, according from conservation of energy. It actually takes the energy from the falling magnet. Hence, B would have a smaller acceleration. It will tend to move slower. Okay, now the term eddy currents here, you don't need to write. Okay. You don't need to write the term eddy currents. You can just say that currents form in the tube that causes heating of the tube. Then the tube heats up. It takes energy from the falling magnet, so magnet B has smaller energy. All right. Okay. This one just on.
Yep. Okay.
Okay, so this one you're okay with it. This one is just the energy explanation. All right.
Yep.
The heating takes energy from your falling magnet, which is actually from your kinetic energy, if you want to think of it another way. The heating energy, the heating takes away energy, takes away kinetic and takes away the kinetic energy of the falling magnet, so it has lower kinetic energy and moves slower. Therefore, magnet B will take a longer time. This is energy explanation. So the last one is force explanation, which is this one. The first 2 points are actually the same. As magnet falls, the aluminum tube cuts the magnetic flux of the magnet. Currents are induced in the aluminum tube. Okay. Right. We can also say EMF is induced, and hence currents are induced in the aluminum tube. This current produces a magnetic field that opposes the motion of the magnet. This one is actually a consequence of Lenz's law. So just now I explained to you step by step, right? You want to, you don't want the flux, you want to oppose your flux change that causes the induced current. So the only way to do that is to oppose the motion of the magnet. You try to prevent the magnet from coming in. You try to prevent the magnet from going out. Okay, so that's why here we say the currents produce magnetic field that opposes motion of the magnet. Therefore, your magnet would have an acceleration less than g, or you can just say that it has smaller acceleration, it moves slower. Okay.
Okay.
So Eddie here don't need to write anything because Eddie will just cause some confusion there, right? So currents are induced in the aluminum tube. Currents produce magnetic field that opposes motion of magnet. So magnet B has smaller acceleration. It moves slower. It will take longer time to fall through. Okay. Have a look at page 15.
Yep.
Right. Page 15. You have a permanent magnets that are now stationed so that metal block oscillates between the poles as shown in figure 3.2. The block is made to oscillate with the same initial amplitude as C. Use energy conservation to explain why the oscillation decreases more rapidly than in D. Okay, now this particular question here is actually, you see this is part E, there's actually some initial part to it. So the initial part of it was actually this one, okay? The earlier part of the question was actually on oscillations, the question of which you have actually done. Basically, what they just said was that you have a beam with a metal block that is placed at the end here. And then after that, during the chapter when we were doing oscillation, we said that this object was actually displaced downward and then released so that it oscillates up and down. And then after that, what followed was the simple harmonic questions. All right. Now, towards the end of this same question, they tell you that the beam with the block attached is now placed between two magnetic poles, as shown in figure 3.2. The block is now made to oscillate with the same initial amplitude as in C. Use energy conservation to explain why the energy of oscillation decreases more rapidly than in D. Now, this one here, the time when we were doing the oscillation chapter, we said that as this thing was oscillating, it will gradually die down. The amplitude of oscillation will gradually decrease because of damping. Okay, so this one was what happened that time when we were doing this question. When we displace the block and then let it oscillate, the amplitude gradually decrease with time. So right now, they're telling you, what if I have the same beam and same block right now? I place it in between two magnetic poles, and then I let it oscillate the same as before. Okay, so what they said was that when I let it oscillate between the magnetic poles, what happened was that the amplitude of oscillation will also decrease, but it decreases much more rapidly compared to before, like this here. So they're asking you to explain why is it right now that when I place it between the magnetic poles, the oscillation seems to have its amplitude decreasing even more. Why is it decreasing even more rapidly? So this one can be explained by the concept of EM induction. What we know is that your metal block is a conductor. And then you have two magnetic poles here and here. Say this one here is the North Pole, this one here is South Pole. You actually have a magnetic field here. So as your metal block is oscillating up and down, you can say there's actually cutting magnetic flux. So when it cuts magnetic flux, you will actually have induced current inside the block itself.
Yep.
Okay, so wait, let me just write this one in. You have induced current inside the magnetic block, right? So when the current is flowing inside the block, it will tend to cause heating. So the heating must come from somewhere. According to conservation of energy, you cannot just have heat coming from nowhere. In this case, the heating actually came from energy of oscillation of the block. Okay, so that's why the answer was like this one. Where this one is I think worth three marks. Some of the things you say here is that as the block oscillates and the EMF is induced in the block because it cuts the magnetic flux of the magnets. Currents are induced in the block that cause heating effect. This heat energy comes from energy of oscillation of the block. Therefore, amplitude decreases. More. Okay. Now the eddy current part, this one I don't think you need to write now. Okay. Now because later on in the AC circuits chapter, I will need to tell you about another term called eddy currents too. So I'll explain it there. For now, this eddy current, just don't bother about it first.
Okay.
Right. So this one is for this. All right. Okay. So can I move on to the next question? If you are okay with this, do you need time to copy?
No, I don't.
Right. Okay.
Yep, I'm good.
Okay, you're good. All right. So next one, this one was page 15. Can I go to page 2? Okay, page 2, this one not yet. Wait, let me have a look at it. 9. Did I do 9? 9 I did. 12, I think I did also. Then after that, 15. Okay, this one I've done. 19. I think it was 6. Wait, let me have a look. That's on the question. Page 6, page 9. Okay, now let's have a look at page 9. Right, page 9 of your worksheet. Right, so now here you have two coils P and Q that are placed close to one another as shown in figure 10.1. The current in coil P is constant. An iron rod is inserted into coil P. Explain why during the time that the rod is moving, there's a reading on the voltmeter connected to coil Q. All right. Okay, so there's this one part here that we also need to explain. Okay, this one has some relation to what we learned. Sorry, this one has some relation with magnetic field. Okay, now last time in magnetic field we said that current through a solenoid produces a magnetic field. Okay, so this is the one thing that we learned in the magnetic field chapter. So what was mentioned was that if you have a solenoid like this, and then I tell you that you have current running through your solenoid, you're going to produce a magnetic field that looks like this, say for example. And this is the basics that we learned in magnetic field chapter. Yep. Now there's one thing that I did not really mention that time also. It's also related to solenoid. This one is that I did not mention to you, inserting an iron core into the solenoid strengthens the magnetic field. Okay, it strengthens the magnetic field. Okay, so if you were to insert an iron core into the solenoid, it will actually strengthen the field. So what we can say here is that B increase or flux linkage actually increase, right? Maybe I just write here. For example, your B would increase, your flux would increase, your flux linkage will increase, any one of this. Okay, so the main thing to note here is that when you insert an iron core into a solenoid, it will strengthen the magnetic field. So the field itself actually becomes stronger. Now, if I have that same solenoid there, like this, and I tell you that my current go up and then down. Now, if I were to put a iron core inside, say right now my iron core is this blue colored thing here. Okay, this blue colored thing here is my iron core. The moment I insert my iron core, my magnetic flux will become stronger. So if just now here you notice that I only have 3 lines, the moment I insert an iron core into the solenoid, because the magnetic field strengthens, your flux density increase, your flux increase, or your flux linkage increase, what will happen is that you look at the magnetic field now would actually have more lines to it. Okay, so if you have more lines, this one is already indicating to you that you have a stronger magnetic field, right? So this is what actually happens when you go and insert an iron core into a solenoid. Okay, so now, right now they're telling you that in your question, you have 2 cores. You have core P, which is over here, and then you also have core Q, which is over here. Now, core P itself is connected to a power supply, okay? But you see here, they mentioned to you that the current in core P is constant. So although we know that this solenoid here has current flowing through it, the magnetic field that it produces by right should be constant. I mean, if let's just say I try to draw the pattern of the magnetic field right now, this is the magnetic field that you have as current flows through core P. And core Q is actually, you can think of core Q as being situated very close to core P, such that the flux from core P will actually link with core Q. Okay, so you can actually think of the magnetic flux from core P as having extended to core Q itself. Okay, because core Q is quite near. All right. So what the question is asking you right now, why is it that when you insert an iron rod into core P, this one here, there's a reading on the voltmeter connected to core Q when you move the rod. Okay, so let's just say right now you look at the current diagram. This one here, the reddish color, this one brownish lines here, this one is representing the magnetic flux before iron core is inserted. When I go and insert the iron core, say I go and insert the iron core here, as I mentioned to you, it's going to strengthen the magnetic field. It's going to cause your lines to become more. It's going to cause the density of the lines to become more. It's going to cause the spacing to become more. Just put it this way, the moment you insert your iron core, your magnetic field strengthens, you expect to see more lines. So here, if I want to represent the lines, let me just draw in green here. Right now, my magnetic field strengthens. I actually now have more lines.
Yeah.
Okay. So what you want to see is this portion here. Let's just say right now the green lines here represent after iron core is inserted. This one is the magnetic field after iron core is inserted. Wait, this one is after iron core is inserted. All right. So now if you look at this blue color section that I highlighted here, you see before your iron core was inserted, there was only one magnetic flux line going through core Q. But after I inserted the iron core, there's now these two additional green lines through core Q. So here, you can actually say that there is actually an increase in flux linkage. Therefore, EMF is induced. That's the reason why you will have a reading on your voltmeter. Because when you move your rod in, for example, you're actually causing an increase in magnetic flux. You have more lines. So these lines actually link to core Q. So any lines linking to core Q is considered to be your flux linkage. So if you suddenly have more lines, you have more flux linkage. So you're going to have EMF induced. Okay.
Okay.
So that's the reason why you have a voltmeter reading here. So this one is June 16 P42. Let me open up the answer for you. June 16 P42 would be this one. Okay, so you explain it based on something like this. Wait, let me see. What question is this? This one is question 10. Okay, so you explain it in this manner. You say that current in core P will produce a magnetic field that links to core Q. When an iron rod is inserted, the magnetic field changes, or you can just say that the magnetic flux changes if you wanted to. Okay, so this causes a change in flux linkage in core Q. Thus, an EMF will be induced according to Faraday's law. This EMF is what your voltmeter is actually measuring.
Okay.
Okay, right. So that one is okay. Then after that, so it's all right. Okay, so can I move on? If this one is
Yes.
okay, all right. Okay, so this one is okay. Then after that, the next one will be just like I did 15 already. Then after that, the next one I'll do is 19. I think 30 also you would have one. Okay, let's just do 19 first, all right. Okay, have a look at page 19. Right, page 19, June 17, P42. Right, that diagram, you probably would have seen it before when you were doing the oscillation chapter. There was a magnet that was oscillating in and out of a spring. So that one is actually a question that you did under the oscillation chapter, but wait, let me see, where is it? Yeah, okay. So here you have a bar magnet of mass 250 grams that is suspended from the free end of the spring. Your magnet is this one, is suspended from a spring. The magnet hangs so that one pole of the magnet is near the center of the core wire. This is your core of wires here. Your magnet is right over here. Okay, one pole is near the center of the core wire. The coil is connected in series with a resistor and a switch, and then they will tell you that the switch is open. The magnet is then displaced vertically and then allowed to oscillate with one pole remaining inside the core. The other pole remains outside the core. At time t equals to 0, the magnet is oscillating freely as it passes through the equilibrium position. At time t equals to 6 seconds, the switch in the circuit is closed. So from here, they are asking you, this part here, they're asking you state Faraday's law of electromagnetic induction. This one I think we can just probably skip it. We can just say the magnitude induced EMF is directly proportional to rate of change of flux cutting or rate of change of flux linkage. This is something from the notes. Okay, now of interest to us is part 2.
Okay.
They tell you use Faraday's law and energy conservation to explain why the amplitude of the oscillation of the magnet reduces after t equals to 6 seconds. So the diagram was this one. We know that the magnet oscillates up and down, and then after that you were given a graph showing how the displacement of the magnet varies with time. Okay, this is what you see. So you see here, at time t equals to 6 seconds, that was corresponding to this point here. At time t equals to 6 seconds, you notice that your amplitude starts to drop. Okay, you see your amplitude is continuously dropping after time t equals to 6 seconds. At time t equals to 6 seconds is actually where you close the switch here. Okay, now from here you should be able to see that my magnet has magnetic flux. As my bar magnet oscillates up and down, the coil is actually cutting the magnetic flux of the magnet. This in turn causes the coil to have induced current. And when the induced current is flowing through my resistor, I have heat dissipated. So this heat dissipated must come from the energy of oscillation of the magnets according to conservation of energy. You see there's some similarity in the answers here. So how you would word it is something like this, where you say that according to Faraday's law, an EMF is induced in the coil because magnetic flux is being cut by the coil as magnet oscillates. An induced current now flows through the resistor and heat energy is dissipated. The energy dissipated comes from energy of oscillations of the magnet. Right, so this one is worth 3 marks, just like that.
Okay.
Okay, right, so this one is okay. Then after that, we move on to.
So basically, the only thing that is extra, I mean, because we've previously learned that when magnetic field is cut, there's an induced current, and induced current will cause heating, and it will
Yes.
cause the mister to it will cause basically it will reduce
the energy of oscillation or whatever you have.
So the extra thing is the magnetic flux being cut, or is the
common thing is always if you read through some of the earlier examples, the common points will always be you saying either magnetic flux is being cut or there's change in flux linkage, therefore got induced EMF. And then after the second thing you say is because got induced EMF, there's induced current. All right. Now from there is where your answers may sometimes change. Okay. The first one is you have basically change of flux cutting or flux linkage. Therefore, EMF is induced. Then the second thing you say is that therefore, because you have induced EMF, induced current flows. Induced current therefore flows. Right? Now, from here, usually that's where your answer sometimes diverges. If you're talking about induced current, sometimes you will notice they say, okay, the induced current causes a magnetic field that opposes whatever the thing it is that opposes necessary motion of the bar or magnet. Then after that, therefore, object moves slower. This one is like the example where we did in the last lesson. You have a bar magnet, you drop it down through some sort of aluminium tube. Then after that, we were explaining why did it actually slow down. So this one we say that because you have induced current, the induced current causes a magnetic field that opposes the motion of the bar or magnet. Therefore, the object will actually slow down. Okay, so this one object moves slower. I need to write my writing properly. It moves slower. Okay, this one was one way in which we could have done it. Here, in our case, because the question says use energy conservation, So we won't use this kind of answer anymore. Instead, we will try to write it in terms of energy. So what we'll do here is probably something like this, where instead we say the induced current causes heating. So the heat energy comes from the motion of the object itself, okay? Which can be an oscillating magnet, which could be a falling magnet, okay? So in terms of what is different, I would say this is where things start to become different, okay? You see the first 2 points as always being common for most of your questions. Yeah, a lot of times you're trying to explain where did the induced current come from, where did the induced EMF come from, and then from there, that's how you got your induced current.
Okay.
Right? Most of your answers that you see so far, they always have this in common. You're basically trying to explain where did your induced EMF, induced current come from, and then it's from there that your answers will start to diverge depending on the context of the question. All right?
Yeah.
So if anything, this part here is where it kind of diverges. No, if you're asking me what was somewhat different, is the ones that are highlighted in orange here. Okay, right. So this one is okay. Right. So there's another one that you will see later on page 30, which also talks about something similar. You will see the pattern there. Let me just look at this one. Okay, have a look at page 30. Okay, have a look at page 30. Okay, state Faraday's law, electromagnetic induction. This one we've done before, so I don't think we'll go through that. Okay, now look at part B. They told you that a coil of insulated wire is wound to one end of a ferrous core and connected to a battery as shown. An aluminum ring is placed on the core. The ring can move freely along the length of the core. The switch is initially open. Then they ask you to use Faraday's law and Lenz's law to explain why the aluminum ring will jump outwards when the switch is closed. Okay, so this one is also something about state and explain. This is what they're saying here and giving you here. So they tell you that in the first place, your switch is initially open. Okay, your switch is initially open. You see here, there's actually a few things, 3 items of interest. You have a core insulated wire, which is this one here, and is connected to a power supply. And then you have an aluminum ring, which is this one here. That same aluminum ring is connected, the aluminum ring and the core insulated wire is connected by this ferrous core here. So here they say that your switch was initially open, and then they ask you, why is it that when you go and close the switch, the aluminum ring will suddenly jump out? So what they're trying to ask you right now is that, why is it that the moment I go and close this switch here, my aluminum ring will actually start to jump out? Okay, so there are a few things that you can somehow deduce from here. Okay, right. So let's just start with something simple first. When you look at the core insulated wire, when the switch was open, is there any magnetic field being produced?
Switch is open.
Yeah, this one is open. No current flows through the coil, right? No current flows through the solenoid, right? So this one, when switch is open, you have no B field, right? Okay.
Yeah.
No magnetic field. But then once you say that you have switch closed, right now the switch is closed like this. So what I'm gonna have is that I have current flowing around through my tube. Current flowing around through my solenoid. in this direction here like this. Okay, so from here, I can actually say that since current is flowing through my coil, I'm going to establish a magnetic field. The magnetic field could probably look like this. All right. But you see, at the same time, your coil has a ferrous core or an iron core inserted through it. So the iron ferrous core has the effect of strengthening the magnetic field. Okay, it has the effect of strengthening the magnetic field. Wait, let me write this thing properly. It has the effect of strengthening the B field. Okay, so while if you don't have the ferrous core, your magnetic field produced by solenoid will probably be just around here. But because of the presence of the ferrous core, what it will do is that it will strengthen the magnetic field. It will actually help to lengthen your magnetic field all the way to here. Okay, you have to lengthen your magnetic field all the way to the edge here like this. Okay, so that's the purpose of your ferrous core here. Is meant to strengthen the magnetic field or to extend the field lah. Okay, if you want to, it's meant to strengthen or extend the magnetic field. So once it's strengthening or extending the magnetic field, you notice that for your aluminum ring, there's now a change in magnetic flux through it. You can just think of it as there's a change in magnetic flux linkage also if you want to. Right, so here, you would have B field through solenoid and the ring. Okay, now the ring itself experiences a change in flux. The ring experiences a change in flux, magnetic flux. Okay, so because previously when you have no current, you have no magnetic field through the ring, your magnetic flux linkage, if you want to, is 0. But now once you close the switch, current is now flowing through the solenoid or the coil. It causes a magnetic field. The magnetic field extends all the way through the ring. So you can say that your aluminum ring experiences a change in flux or flux linkage lah, if you wanted to. Okay. So now from Faraday's law, you know that there is induced EMF and hence current in the ring. Okay, there is now induced EMF and hence current in the ring. Right, so from here, what you can then say here is this. From here, this will start to explain why does your ring tend to jump up in the first place. The answer for this after this was that you have to say that the direction of the induced current, sorry, let me just write it at the top here. The induced current in ring produces a B field to oppose the B field of coil. Therefore, it jumps up. Okay, right. So this one, let me just open up the answer for you. This one is what year? This one is June 18, P41, I think. Okay, wait, let me just give you the full answer first. June 18, P41. Okay, right. So basically the answer was this. They tell you this one. But before I can explain that, maybe I should just explain this one. Okay, now let's just say, for example, we try to look at this in detail first before I go to the answer. When your current first flows in this direction, in the direction of the arrow that I drew here, your solenoid will produce its own magnetic field. Okay, that one we know. So when your solenoid has its own magnetic field, it will have a polarity there. One end will be north, one end will be south. So let's just say, for the sake of our discussion, this part here is north, this part here is south. Okay,
Okay.
so this one we know. And then when we look at this ring here, we know that before this, there's no flux through it. But now suddenly when you close the current, when you close the switch, there's current through it. There's a change in flux. There's an induced current. So what we do know is that over here, we would have induced current. Wait, let me just try and do this one. This one here, you would have induced current. Say I induce. Okay, now this induced current flowing through the ring itself would actually cause its own magnetic field. So the thing here is that when it causes its own magnetic field, you could have maybe two different polarities. Either it is north and south, or south and north here. Okay, so it can have two possible polarities, either this one or this one. All right, but Lenz's law already told us that the induced current will really only flow in one direction because it has to oppose the flux change that causes it. So in our case here, our magnetic, the reason why you have induced current here in the first place was because you have an increase in magnetic flux, right, through the ring. That's why you got your EMF induced and hence current induced. So here, your magnetic field must be in such a way to oppose this increase in magnetic flux. So you can have either two choices. If it was north and south here, this will cause the ring to move upwards. But if it's north and south here, this will cause your ring to move downwards. So which one do you think will actually will actually prevent a further increase in magnetic flux? It should be this one, right? Because this one, you're trying to move the ring as far away as possible from this magnetic field, right? So in Lenz's law will tell you that your induced current will flow in such a way that you have this kind of magnetic polarity. Okay, it cannot be the magnetic polarity on the right, because if it is like this, it will cause your magnet to move even closer. So it will cause your aluminum ring to move even closer to the solenoid. It will cause you to have an even larger increase in magnetic flux. So this one is no longer following Lenz's law. Okay, Lenz's law is always in such a way that you want to prevent the flux change that causes it.
Okay.
Right? So that's why we will say that you have induced current in the ring that produces a B field to oppose the B field of the core. Therefore, it jumps up. All right. So let me just show you the answer. Right. So this is the answer here. I'll rub off some of the unnecessary stuff. Okay, so this one is worth 4 marks, and then these are the workings. You will just say that. Let's zoom in. So what you say here is this: when the switch is closed, current flows in the coil to produce a magnetic flux that links to the aluminum ring. By Faraday's law, changing flux in the ring induces an EMF in the ring. Okay, then from here, induced current in the ring causes magnetic field around the ring. And then last point here is, by Lenz's law, magnetic field around the ring opposes the magnetic field around the coil. Therefore, ring is pushed outwards. Okay?
Okay.
Right. So here, one thing here just now that I mentioned is that most of your questions tend to have a certain pattern like this one, right? Right. So you will notice that the first 2 points are always the same, where you're trying to explain the origin of your EMF, the origin of your induced current. And then from there, it starts to diverge. Either you want to explain the thing in terms of conservation of energy, or either you want to explain the situation in terms of forces. Something is opposing, a force is opposing something. Okay. So in our case here, in our current question here, we were actually using this one into here. Okay. We are trying to explain why the thing moved up, right? So you notice a point that they always use is this one. If you look at your previous question so far, whenever you want to explain explain your answer using the point where you say the induced current causes a magnetic field that kind of slows down the object, that kind of makes the object lose its amplitude even more, the phrase will almost always be the same. You will always say induced current causes a magnetic field that opposes the motion, or in our case, opposes the magnetic field around the cloud. Therefore, it starts to move outwards. Okay. So that's the common point here that you will see. If you want to use Lenz's law, it's always you saying induced current produces a magnetic field that opposes whatever it is that you're doing. Okay. Right here, in our case, in the context of this question, we say that the induced current causes a magnetic field that opposes the magnetic field of the core. Therefore, the ring is pushed outwards. In the previous 2 questions, we said the induced current produces a magnetic field that opposes motion of the falling magnet, that opposes motion of the oscillating magnet. You see there's a similarity there in terms of the phrase. Okay? Right, so this one is this one, right? This one is okay. So let me know once you copy finish, then I'll move on to another 1 or 2 questions.
Okay.
Right, I can move on. All right. Okay, so this one is okay. Then let me just move on to the next one. This one was page 19. Okay, 19 and 30 are done. Okay, I move on to something a bit different or a bit weird right now. Okay, can you just have a look at page 2? Okay, wait on, let me just erase everything up here. Have a look at page 2. Okay. Right, just have a look at page 2 of your worksheet. Here we tell you have a solenoid that's connected in series with a resistor as shown in figure 7.1. As magnet is being moved into solenoid, thermal energy is transferred into the resistor. Use law this one I think we done already. So this one is page 1. I'm not talking about page 2. Sorry. This one. Page 2, question 6, sorry. Just this is under page 2, question 6, this one. Right. Suggest an explanation for each of the following observation. You have an air core solenoid that's connected in series with a battery as shown in figure 6.2. An iron core is inserted into the solenoid. When the iron core is inserted into the solenoid, you have an EMF that opposes EMF of the battery is induced in the solenoid. They want you to explain why is it that as an iron core is inserted in the solenoid, an EMF that opposes EMF of the battery is induced in the solenoid. Okay, this one makes use of some of the stuff that I explained earlier. Wait, this is November 15 P43. Question 6. Okay, now before I go to that, let me just explain a little, very briefly to you what's happening here. Right, same thing as before. You look at what you have. This one is a solenoid. This one is an iron core. Your solenoid just so happens to be connected to a source of EMF. So I know that current will flow through it. Let's just say this current I flows through my solenoid and it produces a magnetic field through the solenoid. This one is one thing that we really know. So say it produces a magnetic field through the solenoid that looks like this green colored line here. Okay, this is the solenoid magnetic field. So now they tell you that you are inserting an iron core into the solenoid and somehow you are getting an EMF that opposes the EMF of the battery. So right now, where do you suppose is your EMF induced, your current is induced? Is it in the solenoid or iron core?
It's induced in the solenoid.
Okay, it's induced in the solenoid. All right. Yeah, okay. The EMF is induced in the solenoid. The EMF is induced inside the EMF and current is induced inside the solenoid. That's correct. But why? Okay, now when you
It's the
go
solenoid that has the magnetic field.
sorry?
It's the solenoid that has the magnetic field.
Yeah, it's the solenoid that has the magnetic field. Okay, you can also say that right now your solenoid has magnetic field or magnetic field through the coils, right? You have flux linkage, right? So right now, say for example, you have your iron core. You go and push your iron core inside here. When you push your iron core inside here, just now earlier I mentioned that it has the effect of strengthening your magnetic field, right? So the moment you push your iron core inside, you're going to cause the magnetic field to strengthen. You're going to have even more magnetic field lines, or rather you're going to have even more magnetic flux now. So say right now it becomes like this, right? The green one was before the magnetic flux, before the iron core was inserted. The blue one is after the iron core is inserted. Now you see here, before, once you inserted the iron core inside, you're going to cause a change in flux in the solenoid, right? Change in flux linkage or change in flux of the solenoid, right? So, maybe I shouldn't draw it here. Let me just shift the diagram a little. Once you insert your iron core, you're going to have change in flux linkage of solenoid. You will say that therefore EMF is induced. Okay, so EMF is induced, current is also induced, because that time I mentioned to you EMF and current are interchangeable. They are closely related to each other. When you have EMF, you have current. So I know that now I have change in flux linkage, I have EMF induced, I also have current induced. But you see, when I look at the current induced, my current induced can also be in two different directions. Okay, in the first place, either it is like this one is my direction of I induced, or it could be like this one could also be my direction of induced current, right? Bear in mind that the pink colored line here is my original current from the battery. Okay, maybe I better just write it properly here. This one is the current from the battery. Okay, so now look at this one. I know that I would have induced current in the solenoid, but which one could be a possible direction? Is it this blue one or the red one?
Mm, should be should be the blue one.
All right, let's just look at what happens if it's the blue one. Okay, if you say that this one is correct, this is the direction of your induced current,
Mm-hmm.
it's in the same direction as my battery current, right?
Mm-hmm.
So this one is going to cause an even larger total current, right?
Yep.
So larger total current, what happens to the magnetic flux in the solenoid?
Will increase.
It will increase, all right? Now, in the
Yep.
first place, how did my induced current came about? Was it because of an increase in flux linkage or decrease in flux linkage? Uh, when you insert the iron core just now, it causes an increase in flux linkage, right?
Yes. Mm-hmm.
That in turn causes you your induced current, right?
Yes.
So you say that your induced current is the blue colored line here.
Mm-hmm.
It's actually in the same direction as your battery current.
Yes.
It's causing your total current to become larger.
Mm-hmm.
It's also going to cause your magnetic flux to become even larger, right?
Yes.
So your flux linkage is going to become even bigger, right?
Mm-hmm.
So is this opposing the flux change that caused the induced current in the first place?
Oh, no, it's not.
No, it's not, right? So you see, then this one
It should be.
is not the correct one. This
Okay.
one here is actually not the direction of current I want.
Okay.
This one instead should be the direction of current I want because it's opposing my battery current. All right.
Mm-hmm.
So therefore, this is the correct one because you see, it's trying to reduce the total current so that my flux doesn't increase even more. Okay, it's opposing my induced current. It's opposing the flux change that caused the induced current. All right. Okay, so that one is the concept behind it. But when you want to write the answer is actually pretty straightforward. You will just say that when you insert the iron core, it increases the magnetic flux in the solenoid. This causes a change in flux linkage. By Faraday's law, an EMF is induced in the solenoid. By Lenz's law, this EMF opposes the battery's EMF. Okay, here just now I explained using induced current, but I can actually also say that you would have induced EMF and the EMF actually opposes the battery's EMF.
Okay.
Because here the question wants you to explain why is there an EMF opposing the battery EMF. I'm just replacing the current with EMF. Same thing.
Okay.
Okay.
Mm-hmm.
So you see, notice that the answers is pretty straightforward. When you want to explain why that, I mean, when you want to explain your answer using Lenz's law, it's always you see this. They just say that the induced current causes a magnetic field that opposes whatever. And then like in your case here, they say, or the induced EMF opposes the battery's EMF by Lenz's law. They didn't really explain in detail how does it do that. They just say, oh, because of Lenz's law, this one will oppose. That's all. Okay, right?